So I said we would be using trigonometry as we're dealing with vectors. And we've been dealing with vectors in the first unit already, and we've actually been doing some vector addition, which is more what we're going to learn about here in this unit where we talk about it in 2 dimensions. So far, we've just been intuitively doing it in 1 dimension. So if you remember the horse problem where we had the horse move forward some distance, and then moved backward some distance. And we figured out what the vector displacement was, and that was from the original position to where you ended up. And we'll talk about the method of how to add these different vectors in more detail in the next video. But so far it's been pretty intuitive because we just take the idea, let's say that's 10 meters, and if we work this green vector backwards was 5 meters, then we just very simply know that 10 meters forward and 5 meters backward would give us a net resultant displacement of 5 meters. So it's all well and good when we have our vectors in this straight one-dimensional plane. However, in reality, vectors can be pointing in all sorts of different directions. So in this video, I'm going to talk about how we're going to deal with vectors when they are not just in one dimension. So I'm going to draw myself a coordinate system here, right? So that we can look at how we're going to do this, right? So if I have a coordinate here, I know that there's all these different quadrants, 1, 2, 3, and 4. And this is from 0 to 90 degrees, and then 90 degrees to 180, and then 180 to 270, and then back to 360. And there are angles in between here. Now, I like to, for my purposes in physics, sort of ignore this idea of quadrant systems, so we wouldn't be dealing with sort of weird angles that we get. I like to use words instead to describe the angle. So I typically only work with angles that are between 0 and 90 degrees. All right, so let's just look at the how I would do this. Okay, so let's say I had a vector here, and it was going. I'm just going to draw it and make up a number, right? So I'm going to make up this number and just say that this is 42 meters. Okay, and at first when we start learning about these, I like to use distance as a vector, or like a displacement as the vector, rather than meters per second or something like that. But remember, there's all sorts of different kinds of vectors. So I'll start with ones that are measured in meters, but I'll actually give you some other examples where things are measured in velocities or whatever kind of vector we want to deal with. And so if I measure, it looks like this angle is about 28 degrees roughly here. Now, how would I describe this angle? There's a couple of different ways that I could describe an angle over here. So we have the positive x-axis, and we have the negative x-axis, or I have the negative y-axis or the positive y-axis. This is one way that I could use to describe the direction of that vector. I could also use directions like north, south, west, and east. Okay, so let's talk about how I could describe that vector in words, right? So I could say that it is 28 degrees above the x-axis. So let's just start listing some of these so you can see, and then I'll do some math. So I could say 42 meters at 28 degrees above the positive x-axis. Okay, that's one way that I could say it. Also, if I just said 42 meters at 28 degrees, I could assume that it was in this quadrant here. I could also say 42 meters, and I could say to the right of the positive y-axis, and so that would be 90 minus 28, which would be 62. 62 degrees left of the positive y-axis. Okay. I could also say that that is 42 meters and it's 28 degrees north of east. So 42 meters, 28 degrees north of east. So if this is east, it would be above it. Okay. Then we could also describe it as 42 meters, and so this, if this is north, this would be east of north. So it would be 42 meters, 62 degrees east of north. Okay, so all those different ways are the same way of explaining this vector, or describing different ways of describing where this vector is located. Now, in order for me to perform vector addition, I'm going to use something called the component method. So with any vector that I'm dealing with in physics, I'm going to break it up into its x and y coordinates. So all I would do is make my vector a right triangle, right? So I am going to draw this side. So this would be part of my right triangle. And I'm going to do it in a marker so you can see it a little bit better. And remember that vectors are arrows. They have a direction. So their components also have a direction. So this would be that much to the right. So that would be the x component of my vector. And then I have the upwards direction. So I would have the y component of my vector. Okay? So this here is my right angle. So you see where the trigonometry comes into play. So here, if I were to solve and I wanted to know the magnitude or the length of my x and y vector, then I would simply just, go ahead and calculate. So if I'm going to do the opposite side over here, I would say the sine of 28 is equal to opposite over 42. And I'll just put opposite so it doesn't look like a 0. So I just take the sine of 28 and then multiply it by 42. And I would get this side is 19.7. And again, remember to make sure that you are in degrees in your calculator. And then if I wanted to find this side, I'd just take the cosine of 28 is equal to adjacent over 42 and figure out that side. So cosine of 28 times 42, right? So 37, and these would be meters. So this vector, the position of this vector, would be 37 meters in the positive y, or in the positive x direction, and 19.7 meters in the positive y direction. Okay? So I would be able to then discern this. So this is the component method. Now let me just go ahead and show you something in a different quadrant. Okay? So let's say I just drew one over here. And it's a little bit longer than that. Let's just ignore, let's not even use displacement. Let's just say this is meters per second. Let's give it a velocity, right? And I'll say that this is, just to keep it sort of to scale, I'll say it's 52 or like 51 meters per second. So again, don't get thrown off if it's not a distance measurement. Distance is pretty intuitive, but we can use any vector that we want. And if I went ahead and measured this angle, see, it's somewhere like, I don't know, about 15 degrees. So the ways that I could describe this vector are 51 meters per second, 15 degrees, and it would be below the negative x-axis, so in this direction. Or I could say 51 meters per second, 15 degrees, and if this is west, this would be south of west. Or I could go from the other direction and say that this is 51 meters per second and say 75, so this would be 75 degrees. And it would be, so if this is south, it would be west of south. Okay? Or I could say 51 meters per second, 75 degrees left of the negative y-axis. Okay? So in this direction. So all those ways describe this angle. Okay? Now I'm going to go ahead and I'm going to draw the components of that vector. So I've got this one. Let me just go ahead and do it with the markers again to make it really visible. So that is my y component. And notice that the arrow is pointing down, and that's going to be important. And then here is my x component. And notice that my arrow is pointing to the left. So now I have myself this little right triangle. Okay? And if I go ahead and I calculate quickly, so 51, or here, let's do this. The sine of 15 times 51 will give me the opposite, so that's 13.2 here. And then the cosine of 51, the cosine of 15 times 51, I knew that sounded wrong, is 49.3 roughly. Okay. But note, based on the angle here and the fact that my vectors are pointing in the negative direction, I actually have to make those vectors negative. Over here to the right was positive and up was positive. Over here then to the left is negative and down is negative. All right? So simply by drawing the vector out and knowing which direction it points determines what the direction of its components as well. And what this does for me is it keeps me from having to calculate this entire angle. If I were to plug into my calculator and I were to use, instead of using 15, I was to use 195, because remember this is 0 to 90 and this is 90 to 180, and so it would be 185. Let's see what happens. So let's take the cosine of 195, and then multiply that times, so I'm doing cosine to this side, so times 51. Notice I get negative 49.3, right? So I can get around having to remember what quadrant it is in and adding up all of the angles just by drawing out the vector components and looking to see if they are positive or negative. And if you do it this way, it's a little bit easier. And in the long run, I think it'll be easier for us to do when we're learning further how to add vectors. So for now, hopefully this clarifies or shows you how to determine and calculate and describe the components of a vector that is not pointing in a straight horizontal or vertical position.